Hello all. This lecture is almost going to be a rerun of the previous lecture because, in fact, that this is the central model that we are introducing. Okay, so but I'll do it in a slightly different fashion this time. So maybe we will not learn too many things which are new in this lecture, but we will try to see whatever we saw earlier in a slightly different perspective. That's all. Okay, so just to recap, what is this hope of machine learning, right? That whatever you do with a group of data, that's known as the training data, which is most of the case only a very small subset of the real data out there. In fact, most of the real data that's out there is not yet generated. Okay, it's going to be generated, but we do this training with a small subset of this data, and using this training data, we make some inference, right? This, like for example, in the standard linear separator examples that we were following, the inference that we make is that, oh, surprise, surprise, I believe, this is what the machine says, I believe that the good data and the bad data are separated by this red hyperplane that I have found out. Okay, and that is a statement. It's a statement that is made based on looking at the training data. But the hope of machine learning is that that statement will hold good even for unseen data, even for not yet born data. That's the hope of machine learning, that this hidden rule that separates good from the bad will hold water. Okay, it will remain true even for new data. Okay, so again, maybe one thing that I did not tell in the last class is, so this is also a question of quite practical relevance, right? Every time you do solve a problem using machine learning, and you are going to deliver this learned model, going to employ this learned model, it is important that the answer to this question, this hope question, is positive, right? It should be that it should generalize to unknown data, new data. So how does one make sure of that? In practice, okay, I'm not saying in theory. In practice, this is often ensured by making sure that from all the data that is available to you, you do not use all of them for training. You use a part of them for training, and then keep some amount of data. The percentages and all may vary. You keep some part of the data outside. Don't give it to the learning algorithm, but keep it only for testing. Okay, so you train your model, find your hyperplane, let us say, for half of the points. That's you give them half the points. Now both, you should again do it probably in a random fashion so that you don't again end up being a bad teacher. So among the data available to you, you use a subset to train and test it on the remaining data. Okay, this is how practically it is done. There are also slightly more sophisticated tricks called cross-validation and so on, where you keep on training it with smaller and smaller subset, one subset of data, test it on the other, then you kind of repartition your data into a different training and testing subset, and then retrain it on that using that part of the data which now you call training, and test it on the other, and so on. This is how it is practically done, because it's important that it is done, right? The real test is on data that was not used to train the model. But in this course, that's not the focus, right? We are not going to reserve some amount of data as test data as opposed to training data to test your algorithm. But we are asking a more deeper question, right? We are asking a very fundamental question as to, can we give a theoretical guarantee? Can we give a mathematical proof that under certain assumptions, okay, what we learn, the knowledge that we learn from the training data will generalize to all data. Okay, it will generalize to real data fairly well. Okay, that is what we are doing. Okay, so this question, whether it will generalize is a important question both in the practical and in the theoretical sense, but we are going to deal with it only in the theoretical sense, okay, which would obviously mean that our how do you say, the range of algorithms that we may be able to handle might be limited, but when we can handle it, then we surely have a very strong hold on this, right? I mean, these are kind of, proven to work classifiers. That's what we would say. Okay. Now, this we also introduced a few terminology to formalize this hope of machine learning. Again, to use the same cliche, right? In formulae. So in the real world, we have a subset of, let's say, Rn. This can be any domain. Since our data is going to reside in Rn, I'm just saying it's Rn. It's usually a very large subset, and you have a binary labeling of the data points. Okay, each data point is labeled either as good +1 or bad -1. What you get to work with, okay, what you get to see is only a very small subset S of this X and the value of Fx on the points in S. You do not know what are the other points, and you also do not know what are the values of F in other points. You do not even know the statistics of F. Is it that F is mostly good, or F is mostly bad, or is it 50-50? Nothing else. All you know is the selected set of samples and the F value at those points. After, during your learning task, or the goal, that what you will do in your office is to return a hypothesis, called G, which is your knowledge line. Okay, this is the hyperline. Okay, hyperplane, or the line that separates is return. We'll call this as the hypothesis returned by the training algorithm, right? So that would usually be a function from the entire Rn to +1 -1. Because surely we want it to generalize, which means we want to apply G to every point in capital X. We do not even know what is capital X. So the only way we can do this is to find this function, this hypothesis function G, from the entire Rn to +1 -1, right? So if you think of Rn, if you imagine Rn in your mind, then G kind of classifies all points of Rn into two, either the good points or the bad points, right? And within the training data, you can actually calculate the performance of G by counting the fraction of points in S which are misclassified by G. Okay, fraction of points in S which are misclassified. Okay, which are misclassified by G. And we would ideally like it to be as small as possible. If the best case is when this error is 0. So this error, for obvious reason, is called in-sample error or empirical error, because what we see is this, right? So this is variously known as in-sample error or empirical error. Okay, and in the cases that we have seen so far, this in-sample error will be 0. But sometime later in the course, we will also handle the case when in-sample error is not really 0, but a small epsilon. Okay, a small value. Okay, but so much is good, right? But now in the last lecture, in lecture 6, what we said is that the hope of ML is not about minimizing En, but it is about guaranteeing that this E out is small. Okay, so what is E out? E out, or what is known as the out of sample error, or some people even call it the true error. Okay, not a bad word. Okay, this is the true error. And the true error, or the out of sample error, is the fraction of points that G will misclassify in X. Okay, so that is the function that we want to keep low. Okay, we want to say that this is very small. Okay, now we know that this will not be possible in general, and even when it is possible, even in the cases where it is possible, we are only hoping that this is probably true. Okay, so we say that, okay, so this E out of G is the outsample error of G, we hope that it will be more than some epsilon with a very small probability only. Okay, which means most likely, so by the way, what is the random process in this whole experiment? When we start talking about probability, we should say what is the random part of this whole process, right? The random part is this choosing this S. Okay, so this S is chosen independently and uniformly from X. Okay, so this is the random, the only part of the whole process, which is probabilistic, right? So whenever we talk about a probability here, it is about choices that result in different SS. Okay, this from the finding G. In the cases that we have seen so far are deterministic algorithms. Perceptron is a learning algorithm, is a deterministic algorithm. SVM is a deterministic algorithm, and so on. Maybe there are randomized algorithms, but we won't deal with that. So in the picture for us so far, the only case of randomness is in picking of S. So this probability essentially is probability resulting out of this randomness. Okay, so we hope that for most choices of S, the out of sample of the resulting G is less than or equal to epsilon. And we also kind of discussed why we can, this is the maximum we can hope for, because there are always bad S's that you can choose. And when you choose S uniformly at random, there is a small probability, it may be very small but non-zero. There is a non-zero probability that very bad training set can come up. We discussed, the malicious teacher example where the training sample, where an adversary picks the S and you can screw up the learning. This can happen accidentally also during a uniform sampling. That is why this guarantee, the hope is kind of diluted. We would not, it is impossible or it is unachievable if we hope that this out of sample error is less than or equal to epsilon every time. We only hope that it is less than epsilon most of the time. And we also know that for this to happen, we need a large enough size for S. Okay, this is the hope of machine learning in formulae. And then what is the key example that we discussed in the last class? So we took a case where your data set, the true data lies in the two-dimensional plane. Okay, and it's though I did not really emphasize it, let me say that the proof that we did in the last class, the one which I'm going to review now, will work only in R2. It will work only in R2, not even, at least I do not know a simple way of extending it to R3. And it will only work when the separating hyperplane or line in this case passes through the origin. Still, again, I'm still trying to generalize it to lines which do not pass through the origin. Okay, so what were the assumptions? X is a large set of points in the plane R2. F is a binary valued function, +1, -1 valued function on the data. We had what is known as the realizability assumption. I think last class I mentioned it as realization assumption. That was wrong. It's the realizability assumption. This time, since I did not want to again make the mistake, I thought I'll at least write it down before I record. Okay. What is the realizability assumption, by the way? It says that X of F is separable by a line through the origin, right? So by a line through the origin, right? So we are in R2, and we also assume that the plus ones and minus ones are separable, are on two sides of a line, and that line should pass through the origin. Okay, and this is what we already know. We do a uniform sampling to get little n points, and this little n can be very small. Okay. Now, what is the guarantee that we finally proved at the end of last class? We proved that if this is satisfied, if this 2 power 2 times 1 minus epsilon power n is less than delta, then we said that every separating hyperplane every separating hyperplane. Okay, so that is important. This was not highlighted in the last class. In fact, that is a very important point, and one of the main reasons that I am kind of doing this lecture as a different perspective of the last lecture is to highlight this, right? So if you ask me, this is the most this is the point that I really want to and invite your attention to. Okay, so like whether by every separating line we only consider lines which are through origin, but among the lines which are through origin we consider every possible separating line of S. Okay, so that is important. Okay, so you have your data, like you have your data that is separable by a line. Okay, you are good from S, you have some good points here and some bad points. Okay, this picture is about S, okay, not X, right? This is what you know. And now what I'm saying is there are multiple hyperplanes through the origin that might separate. Okay, my drawing is bad, but imagine that all these hyperplanes are through the origin. In fact, there are infinitely many hyperplanes through the origin which can separate this S, the plus ones and minus ones of the S that you see. And what we are saying is that all of them are reasonably good. Okay, so that is the idea. All of them are reasonably good. Every separating line through the origin which separates the good and bad points in S has an out of sample error of at most epsilon with high probability, with probability at least some 1 minus delta. Okay, so in mathematical terms, what I want you to pay attention is to this part. Okay, is to pay attention is to this part, right? Our statement is not about one separating hyperplane, but we say that all the hyperplanes which separate S generalize well to true data. Okay, so what we are talking about is a probability of a union of a lot of events. In fact, a union of an uncountably many events, because you have the choice of G. All those G's which satisfy this condition, that ensemble error equal to 0. What do you mean by ensemble error equal to 0? It just means that G correctly separates the points in S. Okay, and this is the event that every such G, okay, you cannot even write it as G1, G2, G3 because it's an uncountable set. Every such G generalizes, right? So this is, if you are saying that even if one G is bad, even if one separating plane that separates your training data S is bad for true data, then your bad event has occurred. Okay, and that we say happens only with a very small probability, less than delta. Now, since this is the point that I really want to emphasize, let me try to justify why we have such a strong requirement. Okay, so this helps us to leave the algorithm part free. Okay, we do not have to insist that the algorithm has to find a particular kind of separating hyperplane, right? So any algorithm which will find a separating plane is good for us. Okay, so this will work for perceptron learning algorithm, this will work for SVM, this will work for even future better algorithms that people may implement. Maybe somebody will come up with an extremely fast new algorithm which would find a separating hyperplane. Whatever be the algorithm, whichever is the thing that is returned, this will work. Okay, so that is the guarantee, right? So we are kind of giving a lot of freedom to the algorithm designer. You really do not bother about any optimal hyperplane or whatever. All you do is go and find out some hyperplane that separates the training data, and mathematics will take care that the rest is okay. Okay, so your job as a programmer is now extremely pleasant. You don't have to worry about which hyperplane, whatever hyperplane that separates will work. That is already guaranteed by the mathematics. Okay, so yeah, that's what I say. Even the worst line that separates S will generalize to X. Okay, and this is needed, right? Now here also again let me recall that this probability that is happening is where is the randomness coming in? Only in the choice of S, not in the algorithm which finds the hyperplane, right? So in the last class, I kind of used a language which may be confusing to some of you. I used the language like, what is the probability that a particular hyperplane kind of makes an error and so on, as if there was some randomness or some random experiment involving choosing the hyperplane. No, there is no random experiment involving the choice of the hyperplane, except indirectly that your choice is limited to those hyperplanes which are separating. Okay, but that is an indirect consequence of what training data S that you produce. So the source of randomness is the choice in S. Okay. So what this statement therefore is saying that most choices of S will give you such a wonderful guarantee that any separator will generalize. Okay. Yeah, and let's do a quick rerun of the proof, okay, which is again, more than we really want to, this example that we saw is a toy example. We worked with R2 and separating planes which are through the origin, but this is only a only a curtain raiser, right? We have to, our search is to find the most lenient conditions under which generalization will work. So this is only a starting point, but there is a lot of things to learn from that. Okay, so what was our proof again quickly in pictures? So this is now the entire data X, okay, the true data. Okay, so this is only for the proof. Okay, so whenever, that's the advantage for us, right? When we are doing the proof, we can assume that we can at least picture the whole X. The algorithm doesn't see this X, but when you are doing the analysis of the algorithm for the proof, we can always start with this picture. Okay, so this is your whole data X, that 10,000 or so data that we have, and that they are, this F is the true hyperplane that separates it. Okay, so now there are again some things that I use slightly vaguely. Okay, F is both a function and a hyperplane. Is that okay? Yeah, so F is this function which assigns +1 to green points and -1 to bad points. Yes, and why do I call this line as F? If I interpret points on the positive side of this line as positive and negative side of this line as negative, I'll get back F. Okay, so since I do not want to introduce too many new variables and so on, I'll say that, okay, this line is also F. But yeah, it's a bit of, there is a slide. So F is one of the separating lines for the true data. Okay, and we assumed that the true data is in fact separable. Okay, that was called the realizability assumption. Okay, and then we kind of identified two angles, okay, θ1 and θ2. So θ1, so angles are, in geometry, angles are counterclockwise direction is what is usually referred to as the positive direction. So θ1 is a positive, the angle subtended by a plane by starting from F and kind of, rotating it in the anti-clockwise direction, in the positive direction. Okay, so you imagine that you have a line, a second line. First you start by putting it over F itself, and then start rotating it in the anti-clockwise, in the positive direction, till the point, and the shaded region, you keep track of the number of data points, the true data points, okay, not the empirical sample. Remember, we are doing a proof. We can kind of, so this what I'm saying now, take a hyperplane, put it over F and rotate it, etc., are not something that the algorithm is doing. These are thought experiments that we, human beings who are trying to make a proof are doing. Okay, so this is not your algorithm. Okay, this is the proof analysis, and this is only a thought experiment. So imagine that now you rotate this brown line, again pivoted to the origin, the origin is kind of pinned down in the counterclockwise direction to a point θ1, where θ1 is the first time you have epsilon n points inside of this shaded region. Okay. Now this shaded region has a nice interpretation. This shaded region is where these two lines will disagree. Okay, this part of the shaded region is on the positive side of F but on the negative side of G, This part of the shaded region is in the negative side of f but the positive side of g. So this is the disagreement region, if I may call it, right? So this shaded region is the region of disagreement. Okay, it is like, different countries, conflicting countries which share a border have different views of what is the boundary, right? What is actual, what is right. So this is the contested area. So we're in our mind, in our thought experiment, we rotate it till your contested area, the region of disagreement has epsilon n points. Now you also repeat the same thing in the clockwise direction, in the negative direction, and theta 2 is the minimum angle that you will have to rotate counterclockwise, so that you will get again epsilon n points. These points will be different from the above points, right? So if you kind of superimpose one on top of the other, you will see that these are actually disjoint regions. Region of disagreement here and region of disagreement here are disjoint. Okay, but apart from that, the idea is the same. Okay, now by the way, how many, for every angle theta, let's say theta from minus 180 degree to plus 180 degree, you have a plane with that angle, right? So again, you may be thinking that this, where is this 360 degrees coming from? You have to think of the normal vector to appreciate the angle, right? This normal vector can be any angle between 0 and 360. So there will be two hyperplanes which are overlapping, one corresponding to a normal vector A and the one corresponding to minus A, but we will treat them as two different lines because the positive and the negative sides are flipped for those two lines. Okay, minor point, I mean, don't worry too much about that. Okay, and yeah, that's what. So when we say there is a hyperplane through the origin, now we can ask what is the angle of that line. It is nothing but the angle from F to G, where counterclockwise is taken as positive. We have defined theta 1 and theta 2, smallest positive angle from F, so that this double wedge region or the contested region has greater than or equal to epsilon n points. Same thing with theta 2. You can also formally write it as this is the fraction of points in the region. That fraction is, okay, let me stick to this equality, strict versus non-strict. I anyway, goof up most of the time, so I'll not worry about that. Yeah, so this is the fraction of points in the contested region is greater than epsilon. Now, this fraction is nothing but the out of sample error. Okay, but okay, this is a proof, but still, okay, this is the out of sample error greater than epsilon, right? So when you kind of rotate your hyperplane counterclockwise, the theta 1 that you get is the minimum theta or the point at which your out of sample error jumps above epsilon. Okay, below, if it was less than theta, the out of sample error was smaller than theta. Same thing with theta 2, but in the opposite direction, you have to go minus theta. Okay, you have to go down. So theta 1 and theta 2 are kind of positive, right? But you should remember that theta 2 is in the negative direction. Okay, and now what is this? I'll collect all such lines, right, which are all those g thetas where your theta is between minus 180 degree and plus 180 degree, right? So if this is your f, then you can go all the way till here or all the way till here, plus minus 180 to 180 degree. So these are set of all lines through the origin, and later we will keep calling this h as your hypothesis class. Okay, this is the class of separators from which you will return an answer. Okay, your algorithm will return an answer, so that is the hypothesis class. Now I divide the hypothesis classes into 3 groups. Okay, now this is a technique that will as far as I can think now, will only work for lines in 2D through the origin. Okay, so this is a very geometric setup and works in 2D geometry. It is quite a challenge to, at least I do not see an easy way to extend it to other cases like lines everywhere, not necessarily through the origin, or even planes through the origin in 3D and so on. So there's a very 2D geometric definition. You classify your hypothesis class into 3 groups. Those where the angle is more than theta 1, more than or equal to theta 1, those which are between minus theta 2 and theta 1, and those which are even further less than minus theta 2, right? So a line, let me draw it in green, right? A line like this green one will be in the third H, right? What did I label the third H as? H2. This will be in H2. Similarly, some line like this will be in H1, whereas a line like this, line like this will be in H0. A line here will also be in H0. The true line F, you see, is also in H0. Okay. Now, those are the three groups. Now, what is key observation here? For every, in the middle part of, middle part of the partition, for every g theta in H naught, your out of sample error is going to be less than epsilon. Okay. In fact, that is how we defined the boundary points between H0, H1 and H0, H2, right? You kept on rotating as long as the out of sample error was within epsilon, you were under theta 1, so it was in H0. The point you crossed it was declared as theta 1, and above that the guys are in H1. Okay. So this is the key observation. Alright, for all those in H0, the out of sample error is less than epsilon. Okay. Now what we are going to argue is that if your S, okay, contains even one point, okay, so let me go back to the picture, right? Now this picture is about the true data. Okay, I kind of, wanted to clean up, and so I erased all the H1s I drew. Okay, but let me say again. Now I'm in my, let me pick a new color again. Okay, something which we do not have. Okay, this purple color. Okay, so if at all there was a purple color that was there, a point was picked in S. Okay, it is in X. If this was picked in S, then you will not have any your learning algorithm, whichever it is, perceptron learning algorithm or SVM, whichever it is, will not pick any point in H2. Okay, will not pick any hyperplane. Okay, this was, I think, H1, right? Any hyperplane in H1, H1, H0, H2. Okay, it will never pick a hyperplane with angle greater than or equal to theta. So the moment you get a data point either here or here or here, right, anywhere in this shaded region, you will never pick any hypothesis from H1, right? Because any hypothesis in H1 is going to misclassify this point, but our learning algorithm are perfect classifiers, so you won't get it, right? So that is the idea. Similarly, any point, if you had picked, from this region, this point or this point, once you have one such point in your S, in your training data, you will never pick any hypothesis from H2. You will not pick any line with angle more than theta. Okay. So this event, right, the event that you might get even one point in this shaded region automatically excludes the entire H1. Okay, it excludes infinitely many possible separating hyperplanes. It excludes entire H1, and moment you get a point here, it excludes everything in H2. Okay, so for any hyperplane in H1 to be still in contention, the random experiment of picking these S points should pick nothing from this region, and that probability is 1 minus epsilon power n. Okay, so the probability that anything in H1 perfectly separates S. Okay, anything in H1 is still a candidate is at most 1 minus epsilon power n. Similarly, from H2 also it is the same thing. Okay, where did the 1 minus epsilon come from? Because the epsilon fraction of points are in that shaded region. every time, in order to avoid them, the probability is 1 minus epsilon. Since the trials are independent, you will get a n. By the way, this probability is almost equal to, I did not want to write that because there are some round off errors due to epsilon n not being an exact number and so on. So maybe we will not be able to achieve epsilon. That is why we kind of wait for the first time we cross epsilon. Okay. So for all practical purposes, this is an equality. Whereas in the last class, I kind of made a mistake by analyzing for a single hyperplane. I almost wrote it's an equality. That is not true. For picking any single hyperplane, we do not know, because we do not know this which algorithm, what algorithm you are going to use and so on. Okay. Yeah. Now, what about H2? The same thing, 1 minus epsilon. Again, it's almost equal to, and we now use the union bound, the probability that the S can be separated using a hyperplane from H1 or H2 is at most the sum of these two, which is this number. So, the only way your out of sample error can be greater than epsilon is if you pick a plane from H1 or H2, right? These are the only two ways in which your out of sample error can be more than epsilon. If you pick anything from H0, your out of sample error that's the observation. If you pick anything from this, then the out of sample error is less than epsilon. Okay. So the probability that you pick, this is the probability of H1 union H2. That is nothing but the probability that any hyperplane, okay, probability that any hyperplane with ensemble error 0, right? Why? Because this set, this union, this G element of, okay, again, same color is not a good idea. Okay, what I am saying is that this set, all those hyperplanes G, subset of H, G element of H, such that ensemble error of G is equal to 0 is nothing but those which are in those E of G and E out of G greater than epsilon, right? So these are in nothing but H1 union H2, and we are saying that this will happen only with this probability 2 times 1 minus epsilon power n. Okay, so now we have a bit more of calculus to do to express the size of training data as a function of epsilon and delta. Okay, or in other words, solving for n in terms of epsilon and delta. So what we need is this guarantee that twice 1 minus epsilon power n is less than delta. So in when you are looking for this inversion, solving for the minimum n, which will give these guarantees, you are a kind of working an implication chain backwards. Okay, you want to kind of simplify this algebraically, but then it is not like solving for an inequality in the usual sense. You have to kind of work backwards. Okay, so this is what we want. Okay, we want this. Okay, we want this. We will get it. We want this. We will get it if this is true. Okay, by the way, why is this true? 1 plus x is always upper bounded by e power x. So if this an upper bound to this is less than delta, the left hand side of line 2 is an upper bound of left hand side of line 1. So if an upper bound is less than delta, this will also be less than delta. Okay, by the way, 1 plus x, how do you prove it's less than e power x? In fact, this is a very, very simple inequality, but gets used a lot of times. And remember, it is true for all x, positive, negative, everything. In fact, this is actually I should write this less than or equal to, because when x equal to 0, they touch. Okay, so how do you prove that? The best proof that I have seen is pictorial. For you plot the left hand side. The left hand side is 1 plus x. Right. So when this is x, this is 1. Okay. So the black line is Okay, let me draw 1 plus x in red, and now I will draw e power x in green, right? So yeah, this is how the e power x curve goes, right? And again, we can say that you can prove this more formally by using the derivative and so on. But this is the picture proof of this inequality. This is a very, very useful inequality to know. Okay, so that's what we have used here. Now, just a rearrangement of terms. This will happen if 2 to the e to the power epsilon n is greater than 2 by delta n, or finally n greater than 1 by epsilon times the natural logarithm of 2 over delta. Okay, so if you have at least these many training sample, if you have more than 1 by epsilon times ln 2 by delta training sample, then we have a guarantee that with a probability at least 1 minus delta, every separating hyperplane for the training data will generalize with an out of sample error at most epsilon to true data. Let me repeat that again. If you choose at least these many training samples in the fashion, in the uniform fashion and so on, then every hyperplane, okay, let me again say every hyperplane which separates this training data will, with very high probability at least 1 minus delta, generalize with a very small error to true data. By small I mean error less than epsilon. Okay, so that's what I have written down more formally here as a theorem. This is the setting. This whole thing is just the statement of the theorem. I have just wrote it in 3 colors for clarity. This is the setting. Let x is be a subset of r squared, and f is a binary function on x, which are separable by a line through origin. This is the realizability assumption through the origin, and for any epsilon delta greater than 0. Okay, so this might come as a surprise to you, right? Suddenly it looks like a calculus kind of a language, right? But that's what, when we keep epsilon and delta as variables, this is what we get. These are known as quantitative guarantees, right? So how much true error can we live with may be dictated by the application. There might be some applications where you can live with 1% error, in which case epsilon might be 0.01. And there might be some applications where we can only live with 1 in a million error, in which case epsilon will be 10 power minus 6. The same thing for delta. Okay, sometimes we want our sampling and the resulting learning algorithm to succeed with very high probability. Sometimes we are not that critical. Okay, that is the delta factor. So the user can choose epsilon and delta, but depending on the epsilon and delta, they will have to pay a price. Okay, in fact, the price increases linearly with 1 by epsilon, right? So if you want 10 times more accuracy, you will pay 10 times more, have to pay for 10 times more training data. Delta is a bit more tolerant. It doesn't increase linearly with ln with 1 over delta. It only increases with the logarithm of 1 over delta. Okay, so this is slightly more friendly term. Yeah, but the point is that whatever epsilon and delta the user picks, if you agree to use at least these many samples sampled independently and uniformly from the true data, then with probability at least 1 minus delta, every line through the origin. Okay, again let me highlight this. Okay, every line through the origin that separates S also separates at least 1 minus epsilon fraction of points in X, or the true error, the out of sample error is at most epsilon. Okay, this is the theorem that we proved in one class and revisited again. So I hope it's not this particular theorem that is important, but this line of attack we are now going to use some 4 or 5 more times. Okay, that is why I thought it was important to say that again. Okay. Now, observe that in this whole theorem and never in the proof, the size of x appeared, right? The size of x was mysteriously missing, right? So, for example, even this number of points, though I kept saying it's a large number of points and so on, the largeness of it was never used. It could actually be smaller than your training data. Why? Then how do you get n training data? Remember that we were sampling with replacement, right? We were sampling with replacement. So even if you have fewer than n points, it is fine. By the way, once your training data contains all the test data, your true error will also be 0 because your in-sample error is 0. The out-of-sample error, since there is nothing now outside, it will also be 0. This minor point. More importantly, actually, your X could have been an infinite set. No, there was no problem because we did not use the size of the infinite set, except for a minor point. It is very difficult to do a uniform sampling from an infinite set. Right? For a uniform sampling, we have to give the same probability to every point in the set. So if you give a non-zero probability, then the probability won't add up to 1. It will add up to infinity. And if you give 0 probability, the same issue. It won't add up to 1. It will only add up to 0. Right? So that's the only catch there which prevents us from X being infinity. But we would generally, there is very strong reason for us to prefer that your X should be all of R squared. Why? Because as I told you, most of the unseen data is not just unseen. They may be unbound. They are unknown. So in most applications, we really do not know where X comes from. And hence, knowing this X and sampling it may be difficult. Okay, so that is the first change that we are going to introduce into this model. Okay, we'll introduce multiple changes in this model. This is the first change, and this first change will lead us to what is known as a PAC model, or a probabilistically approximately correct model. That actually, the name comes from this guarantee here. Okay, this guarantee that you are probabilistically correct. You are probably correct. You are correct with a probability at least 1 minus delta, and even then you are only approximately correct because you may make an error of epsilon. Okay, so the probably approximately correct comes from that. Okay, so this is the probably approximately correct model. Okay. So what is the change? Change is that your X is no more a given finite subset of R squared, but there is no X after all, in fact, in the new model. But what you have is a probability distribution on R squared. Okay, so there's a 2-variable probability distribution. You might have learned many examples in your probability class, right? You can probably take a centrally symmetric Gaussian with mean 0 and variance some sigma 1 and sigma 1 on both axes, right? That's one thing that you can imagine. Another thing is that you can identify a bounded region, let us say the unit square, and then say that the probability distribution is uniform inside this unit square and 0 everywhere else, right? Or you can kind of find a very crazy region and say that okay, this observe some kind of weird distribution on this, right? In fact, you can even give discrete distributions on continuous domain like R squared, right? You can maybe identify a collection of some 10,000 points, right? Some 10,000 points in R squared, and say that each of that point appears, this distribution is like each of that point has probability 1 by 10,000, everywhere else it is 0. In which case this will reduce to the problem that we studied, okay? But this is very rare. Most of the time, the distribution that we assume will be a continuous distribution. Okay, and what is S? So we still do not know. Now there is no notion of X. Okay, X has gone out of picture. The role of X is now replaced or taken over by this distribution D. Usually given as a join PDF. Okay, it will be given as a 2D, a join PDF on R squared. And your S is n independent samples picked according to D. Okay, so each sampling of S is from D. And our true error, when we are going to estimate our out of sample error or true error, we will also estimate it assuming that the real data also is coming from the same distribution D. Okay, so that's what we are doing, right? We kind of make this assumption to evaluate E out. So what will be E out? This would be the expectation that G is not equal to F, and since this G not equal to F is a true false event, either it is equal or not equal, this expectation is nothing but the probability that they disagree. Okay, or now the probability is not a number of points or the fraction of points where they disagree. This is some sense a measure of that set where they disagree. Okay, so remember this, when I say xn is an element of D, I should have rather said, I should have rather said x is sampled according to D. Okay, so x can be any point in R squared, but you don't get to pick a point arbitrarily. You have to pick it according to D. So if it's a centrally symmetric Gaussian, you are more likely to pick an x that is closer to the origin, and so on, right? And what is this probability now? This is the measure of that region where G and F disagrees. Okay, so again, since this is the only change, let me kind of say two cases. If D is discrete, then this is nothing but you sum all the PMF values. Okay, let's say PD is the if D is a discrete distribution, it can be modeled by a probability mass function, in which case this is nothing but you sum the probability values under D for all the misclassified points. That would be your E out. This is like what we were doing so far, but in the more general case, you will have to kind of find the measure, the probability measure of that region of disagreement, of where your function and the true function disagreed. Okay, so like for example in R2, let us say there was a small region like this where F and G were different. What is E out of G is the probability measure of this region. Okay, so you integrate your PDF in this region. That's what is done here. If you integrate your join PDF in this region, what it gives you is the out of sample error. Okay, and this is the standard model. We wouldn't work with this model of having a true data X, but it's a helpful thing to have. Okay, so yeah, I mean this is a good point to stop. In the next class, we will try to do further relaxations to the PAC model. Thank you.